Okay guys, here we are in part 2 of our adventures of graphing rational functions. So Mr. Bronson talked to you about all the different steps we take and all the different things we're going to graph on the rational function graph. However, there's going to be one extra piece today, and that is when we get a hole in the graph. Now, that sounds kind of weird. What's a hole in the graph look like? Well, imagine a piece of ribbon that someone just takes a hole punch and just punches a hole out of it. That's what it looks like, which is kind of strange looking, but we'll get to that. So when do we get a hole in the graph? Well, we get a hole in the graph when we have a factor that is on the top and the bottom of the rational function and therefore can be reduced, crossed out. So for our purposes, for all of the points and asymptotes we're going to graph, we're going to use the reduced function. However, we need to remember that the original function, it originally included x minus 2. So that means that we can't plug in any value that makes x minus 2 equal to 0 because I can't have a 0 on the denominator all the way from the very beginning. So we will get to that second step here. So the first thing we want to do is to find our vertical asymptote. And a vertical asymptote is a block saying, sorry, that value of x can't be allowed into the function. Now, why would we ever exclude a value of x? Well, in this case, if our denominator equals 0, that's a problem. So we can't plug in any value that's going to make our denominator equal to 0. So I'm going to set the denominator equal to 0 and figure out what that value of x is. Right? And it looks like the value of x that we have to exclude for our vertical asymptote is x equals 5. So I'm going to come over here and I'm going to draw a vertical asymptote, which is a dashed line, right? And this is a block. We're not allowed to have x equals 5 in our graph, right? Because that would cause it to be undefined. Okay, so now we talked about this hole thing, right? So a hole, we have a hole at x plus 1 equals, sorry, not x plus 1, x minus 2 equals 0. Right? So that means if I were to take the value, in this case 2, and plug it in to the original function, I would get a 0 on the bottom, which isn't okay. So the thing about a hole is, though, it's an actual ordered pair. So I need to plug in x equals 2 to get the y value of the hole. Okay, so let's do that. So I'm going to say y equals, I'm going to go up here and plug it into my reduced function. So that looks like 5 over negative 3, which is about negative 1 2/3. Not about, it actually is negative 1 2/3. So that means my hole is at 2 comma negative 5/3, or I can write negative 1 2/3, doesn't matter. So let's see what that looks like. Like I told you, it just looks like a little hole. So I'm going to say 2 comma negative 1 2/3 is about there. So I just graphed my hole. Now my horizontal asymptote, if you guys remember, is I'm going to compare the degree of the numerator and denominator. Okay? So the degree is the highest exponent that each of them has. So it looks like x to the first on both of them. Right? So when the degrees are the same, like in this case, I'm going to make a ratio of the lead coefficients. So in this case, both my lead coefficients are 1. Right? So I'm going to say y equals 1 over 1, which is just 1. Now a horizontal asymptote is a dashed line, but instead it's going horizontally. So I'm going to go from here where y is 1 all the way along here. So there's my horizontal asymptote. Okay, so we have our hole, but we need some other points. So the x-intercept, if you remember, an x-intercept is where y equals 0. So let's make y 0. 0 equals x plus 3 over x minus 5. Actually, there's not enough room here, sorry. Let's do it down here. An x-intercept is where y equals 0. So I'm going to say 0 equals x plus 3 over x minus 5. So what happens when I multiply both sides by x minus 5, right? To get that x minus 5 to cancel. I'm left with x minus 5 times 0, which is 0. And it's just the numerator that's going to determine my x value. And we know that the y value is 0. We just made it 0. So negative 3 comma 0 is my x-intercept. So I'm going to graph that right here. And if you remember, guys, a y-intercept is where x equals 0. So let's make x 0. 0 plus 3 over 0 minus 5. So that gives me y equals negative 3 fifths. So I've got 0 comma negative 3 fifths. And that's about right there. Okay, so now I've got some points, including my hole, and I'm ready to draw my graph. Now here's the thing, guys. This x equals 5 splits my graph into 2 pieces. So this is the image I like to use here. Imagine these asymptotes are walls, right? And so now we have 4 rooms. We have the bottom left room, the upper left room, the upper right room, and the bottom right room. And imagine these points are mice, and the room is dark, right? So what happens when I come into this bottom left room and I turn on the lights? Well, when you turn lights on and mice are in the room, they're going to run towards the walls. So the graph is going to be, it's going to go through all 3 of these mice, and it's going to run towards these walls but not cross over them. So this is the bottom part of the graph. Now we don't have any, none of our mice landed in either of the right-sided rooms. So what I need to do is I need to find another point. I don't know whether my mouse is going to end up here or down here. So if this is x equals 5, let's just make x equals 6. We just need a point in this side of the room. So I'm going to plug that in. Now I could have done 7, 8, 9, 10, whatever. I just am trying to keep it simple here. So when I simplify this, I get 9 over 1, which is 9. So there's a point also at 6 comma 9, which is right up here. And I only need 1 point because I know that the graph is going to go towards the walls, right? And there is no graph. It can't cross over this y equals 1. So this is our final product here, our final graph. Okay, so domain, if you guys remember domain are all the x values that are allowed into our function. So it looks like every x value is going to be okay, except for the ones that either were vertical asymptotes or holes, right? Because we can't have the denominator equal to 0. So I have to say, okay, all real numbers, but x cannot equal the x value of our vertical asymptote or the x value of the hole. Now the same thing's going to happen with the y, right? We can't, right? If you notice this graph, it didn't cross, no point is at y equals 1 because it's a horizontal asymptote there. So y can't equal 1, and then also y can't equal the y value of the hole, right? Because we had to exclude that. So this is what our graph looks like. It's always going to have pieces like this. So if none of your points end up in this right-sided region or left-sided region, you need to plug in a point to get another value to get some point there. Okay, let's try another one, then we're done. Okay, this one's the same type of thing, but it's going to require us to factor. So if you guys recognize this pattern, this is diamond factoring. 2 numbers that multiply to -5 and add to -4 would be -5 and 1. So this turns to x minus 5 times x plus 1. And then on the bottom, we have two numbers that multiply to 3 and add to 4, which would be 3 and 1. Ah, look guys, the same. I'm going to get a whole again. Right? If you notice, there's an x plus 1 on the top. Now I can't cross the x squareds off here because they're terms. I can only cross off factors. So I can cross off the x plus 1, and here is our reduced function that we are going to use for all plugging in purposes. But now we know there's going to be a hole caused by this reducing. Okay guys, a VA, I'm going to take my denominator and set it equal to 0. So x plus 3 equals 0 means that my VA is that x equals negative 3. So I'm going to come along here, draw my VA, and x equals negative 3. Okay, now we also know we got a hole, we crossed off x plus 1. So that means the x value of our hole is going to be at whatever value of x makes x plus 1 equals 0. So in this case, my hole is at x equals negative 1, but I need to find the y coordinate of the hole. Right? And I'm going to do that by plugging in x equals negative 1. So y equals negative 1 minus 5 over negative 1 plus 3. That one worked out nicely. Negative 6 over 2, which is negative 3. So my hole is at negative 1 comma negative 3. So I'm going to go graph that right here. Yep, that's right. Okay, horizontal asymptote. I'm going to compare the numerator and the denominator, the degree of the numerator, the degree of the denominator. Looks like they're both x to the first, and they both have a lead coefficient of 1. So I'm going to say y equals 1 is my HA. Now both of these happen to be y equals 1, but it's not always like that. Okay guys, x-intercept. An x-intercept is where y equals 0. So x-intercept, y equals 0. So I'm going to have 0 equals x minus 5 over x plus 3. So let's multiply both sides by x plus 3. And I get 0 equals x minus 5. Okay, so it looks like my x-intercept is at x equals 5. And of course we made y equal to 0. So 5 comma 0 is my x-intercept. Okay, and my y-intercept is where x equals 0. So I'll come over here for the y-intercept. The y-intercept is where x equals 0. So I'll say y equals 0 minus 5 over 0 plus 3. And that equals negative 5/3. So 0 comma negative 5/3 is my y-intercept. So that's right about here. Okay guys, here we are. We've got mice on this side of the VA, but not over here. So we need to plug in another point to figure out where our graph is going to be. Is it going to be in the upper left or the upper right? Well, let's check. Let's plug in, I don't know, how about x equals negative 4? Right, we want to figure out, are we going to draw a point up here or down here? So y equals negative 4 minus 5 over negative 4 plus 3. So that's equal to negative 9 over negative 1, which is 9. So we also have a point at negative 4 comma 9 up here. So now, guys, we're ready to draw our graph. We know our graph goes through all of the points and then heads towards the walls. Can't cross over these asymptotes. And then up here, we have the same thing, and it heads towards the wall. So that's our graph right there. Okay, guys, domain, we're almost done. The domain are all the x values that are allowed into our function. So we're allowing all of them in, so all real numbers, except x can't equal either of these values, the whole or the vertical asymptote. Right? And I can see that on the graph, right? I can see there's no x value at -1, and I can also see there's no x value at -3. How about the range? Well, the range, we're also okay with everything, except if you look here, I don't have any y values at y equals 1, and I also don't have any y values at the whole, the y value of the whole, because I have to exclude that. Okay, guys, thanks for listening. See you guys next time.